Hey everyone, welcome back to another exciting video. Today, we're going to talk about session hijacking, a technique attackers use to take control of someone's session and bypass their login. By the end of this video, you'll learn what session hijacking is, how it works on apps and networks, tools hackers use for session hijacking, and most importantly, how to protect yourself from it. Alright, let's break it down. What is session hijacking? When you log into a website, the server gives your browser a session token, like a unique ID, to keep you logged in. But here's the risk. Attackers can steal or guess that token to take over your session without needing your password. This attack works because authentication usually happens only when you first log in. Once the session is active, hackers can hijack it to steal sensitive information, impersonate you, or even disrupt the connection. Session hijacking can lead to dangerous attacks like man-in-the-middle. It is when hackers secretly intercept communication between you and the server. And the other is denial of service. This is when disrupting sessions to crash services or steal data. So, session hijacking lets attackers pretend to be you, causing identity theft, fraud, and more. Stay tuned as we explore how this happens and how you can protect yourself. Alright, now let's talk about why session hijacking is so successful. First up, no account lockout for invalid session ID. Imagine this. A hacker tries guessing your session ID over and over, but the website doesn't stop them or even flag the suspicious activity. This gives the hacker endless chances to get it right. It's called a brute force attack. And since the server doesn't complain or send any warnings, the attacker can eventually crack the code. Next, weak session IDs or predictable patterns. Some websites use simple methods to generate session IDs, like combining timestamps or IP addresses. This makes it easier for attackers to figure out the pattern and guess the ID. And even if a strong algorithm is used, short session IDs can still be cracked quickly by trying out all the possibilities. Now let's talk about how session ID are handled. Here's the deal. If session ID aren't protected properly, attackers can trick your browser into exposing them. They can use methods like DNS poisoning, cross-site scripting, or even exploit bugs in your browser to grab that session ID. Once they have it, they're in. Another issue is indefinite session timeouts. You know that Remember Me checkbox you see on websites? It's super convenient, but can also be risky. If a session ID doesn't expire, hackers have all the time they need to steal it. Plus, if they get access to your cookies or a vulnerable proxy server, they can hijack your session even faster. Now here's a big one, TCPIP vulnerabilities. Most computers rely on TCPIP for communication, but unfortunately, this system has some built-in design flaws. These flaws make it easier for attackers to intercept and manipulate your sessions. Finally, lack of encryption. If websites don't encrypt their session ID properly, it's like handing over the keys to your car on a silver platter. On unprotected networks, attackers can sniff out these IDs with ease. Even websites using SSL encryption can be vulnerable if the session ID itself isn't secure. So to sum it up, weak security measures, predictable patterns, and poor encryption make session hijacking a powerful tool for attackers. But don't worry, up next, we'll talk about how these attacks happen in detail and how you can protect yourself. Alright, let's talk about how session hijacking actually works. Think about this. It's much easier for an attacker to slip into a system by pretending to be a legitimate user than trying to break in from scratch. If they can find an active session, they can take it over, stay connected for hours, and do whatever they want without raising suspicion. Here's how they do it. First, the attacker tracks the connection. They use tools like network sniffers to monitor the data being sent back and forth between a user and a server. The key here is figuring out the sequence and acknowledgement numbers that the session relies on. These numbers are what keep the communication organized and secure, but if the attacker gets their hands on them, they can start crafting fake packets that look exactly like they're coming from the legitimate user. Next, the attacker creates a bit of chaos by desynchronizing the session. This means they disrupt the communication between the user and the server, throwing them slightly out of sync. Imagine sending a flood of meaningless data to the server, just enough to confuse it. The server's sequence numbers move forward, but the user's side doesn't realize this. Now, the server and user are no longer on the same page, and the attacker can step in. Sometimes, the attacker might use a reset flag to force the server to close the current connection and open a new one. And guess what? That new connection is now controlled by the attacker. Both the server and the user still think they're talking to each other, but the attacker is right in the middle, watching everything and even changing the data being sent. Once they've hijacked the session, it's game on. They can send commands to the server, pretend to be the user, steal sensitive information, or even act as a middleman, relaying and altering the communication in real time. The trickiest part of all this? It relies on exploiting the way TCP connections work, specifically the three-way handshake that establishes a session. If the attacker can guess or sniff out the sequence numbers during this handshake, they can slip right in. It's a clever but dangerous process. And while desynchronization is a key step, it doesn't always go smoothly. For example, if the attacker makes a mistake, the server might respond with a flood of acknowledgement packets, creating a storm of network activity that could expose the attack. But when done right, it's almost impossible to detect until it's too late. So that's how session hijacking works. The attacker tracks the session, disrupts it just enough to take control, and then uses it to their advantage. Pretty scary, right? All right, let's get into the types of session hijacking and how attackers approach this sneaky method. There are two main types: passive session hijacking and active session hijacking. The difference? It's all about how involved the attacker gets. Let's start with passive session hijacking. This is where the attacker hijacks a session but stays in the background, quietly observing everything that happens. Think of it like someone listening to a private phone conversation without saying a word. They use tools like sniffers to capture all the data flowing through the network. This can include sensitive information like usernames and passwords. Once they have that, they can use it later to log in as if they're the legitimate user. It's a subtle attack, but incredibly dangerous because you often won't even know it's happening. For example, an attacker might grab your login credentials and save them for later. This gives them full access to your account whenever they want. Scary, right? Now, countering passive hijacking mostly involves encrypting your data. Tools like Kerberos or one-time password systems can help. But here's the catch. If the data isn't encrypted or doesn't have a digital signature, passive attacks are hard to detect and almost impossible to stop in real time. Now let's move to active session hijacking. This one's more aggressive. The attacker doesn't just observe, they take control. Imagine someone barging into your conversation and pretending to be you. That's exactly what happens in an active hijacking attack. A common example of this is the man-in-the-middle attack. In this scenario, the attacker sits between you and the server, intercepting all your data while pretending to be either side. It's like someone secretly acting as the postman, reading your letters, and even rewriting them before they're delivered. To pull this off, the attacker needs to predict something called a sequence number, which is like a key to your session. But here's the good news. Most modern systems make this hard to do. Operating systems now use random values for sequence numbers, so it's not as easy as it used to be. So passive hijacking is all about spying, while active hijacking is about taking over and interfering. Both are dangerous, but they work in very different ways. All right, let's break this down and dive into spoofing versus hijacking in a way that's super clear and easy to understand. Now, session hijacking and spoofing may sound similar, but they're actually different methods attackers use to mess with network connections. Think of it like this. Spoofing is about pretending to be someone else, while hijacking is about taking over something that's already in progress. Let's start with blind hijacking. It's a pretty sneaky tactic. Imagine an attacker who can't see the actual responses from the server or victim. Instead, they rely on predicting sequence numbers, which are like digital markers in a connection. Here's the thing. In every TCP session, sequence numbers are used to keep data flowing in the right order. Attackers try to guess these numbers to trick the server into thinking they're part of the conversation. But there's a catch. Blind hijacking requires some serious guesswork because the attacker doesn't have direct access to the data going back and forth. They can't just sit there and watch replies. It's more like playing darts in the dark. Now let's move to IP spoofing, which is a bit different. In this scenario, the attacker pretends to be someone else entirely, like a trusted user or machine. Instead of waiting for a session to already be active, the attacker starts fresh by using stolen credentials. It's like walking into a secure building with a fake ID. What makes spoofing easier is that it doesn't always involve guessing sequence numbers. If there's no active session tied to an IP address, attackers can bypass that step entirely. However, for session-related spoofing, like when they try to hijack a connection, they still need to figure out those pesky sequence numbers. So how do these methods play out in real attacks? In a session hijacking attack, the attacker waits for someone else to establish a connection, like James logging into a mail server. Then the attacker, let's call him John, steps in. John might use a denial of service attack to kick James out of the session and then seamlessly take over, acting as if he's James. To pull this off, John needs to know the sequence numbers and the exact status of James's session when he takes control. It's complex and takes a lot of effort. On the other hand, in a spoofing attack, John doesn't need to hijack an existing session. He can create a new one by pretending to be James from the start. While this may seem simpler, it's still no walk in the park. It often requires root access to craft special packets or knowledge of trust relationships between machines. So spoofing is about faking identity, often to start a new session. Hijacking is about taking over an active session, displacing a legitimate user, and acting in their place. Both methods have their challenges, and modern security measures like encryption, integrity checks, and strong authentication can make these attacks nearly impossible. All right, let's talk about session hijacking in the OSI model. Don't worry, I'll break it down so it's easy to follow. When we talk about session hijacking in terms of the OSI model, there are two main levels where this can happen: network level and application level. First, let's look at network level hijacking. This is all about intercepting data while it's being transmitted between a client and a server. Think of it like someone tapping into your phone line while you're on a call, listening in, and gathering all the details they need to impersonate you later. What makes this level popular with attackers is that it doesn't focus on a specific web application. It targets the underlying protocols, like TCP or UDP, which almost all applications rely on. Once they succeed, they've got the foundation to go after your application-level sessions too. Now moving on to application-level hijacking. This is where attackers take things a step further. Instead of just observing, they go after your session ID. With that session ID in hand, they can hijack your existing session or even create new ones to gain unauthorized access. What's even scarier is that both levels often work together. An attacker might start at the network level to get the initial data, then use that information to jump into the application level and take over your session completely. All right, let's break it down and take a closer look at application-level session hijacking and all these methods attackers use to compromise session tokens. This is where things get interesting because it's all about how attackers target web applications by going after the session IDs. Now, in application-level hijacking, attackers aim to steal or guess these session tokens, which are generated by servers to identify and authenticate users. If they get hold of a session token, they can hijack an active session or even create a new one without your knowledge. Here's how attackers can get their hands on those tokens. First, there's stealing. This is where attackers directly take session IDs from your system or the server. It's like breaking into your house and grabbing the keys to your car. If they have physical access to your device, they might look for session files stored in your browser or memory. But most of the time, attackers use tools like Wireshark or Riverbed Packet Analyzer to sniff the network traffic between your device and the server. By analyzing this traffic, they can extract the session IDs hidden inside the packets. Next up is guessing. Some servers use weak algorithms to generate session IDs, making them predictable. Attackers observe patterns in these session tokens, like how they increase sequentially, and then try to guess a valid one. Now, this isn't always easy, but when servers don't randomize their session tokens properly, it can become a big problem. Then there's brute forcing, which is a more aggressive approach. Attackers use software to try every possible combination of session IDs until they find one that works. Think of it like trying every possible combination on a lock. With a fast internet connection, an attacker can try thousands of session IDs per second, especially if the server's session ID generation algorithm is weak. If the range of possible session IDs is small, this is called a session prediction attack. Let's discuss how attackers compromise session IDs using techniques like sniffing and prediction. A session ID serves as a unique identifier that the server assigns to track your session. Attackers aim to exploit this by intercepting or guessing these tokens. When it comes to sniffing, an attacker uses tools like Wireshark to monitor the communication between a user and a web server. If the traffic isn't encrypted, such as when using HTTP instead of HTTPS, it becomes relatively easy to capture session tokens. Once the attacker identifies the token in the intercepted packets, they can impersonate the user by sending the stolen token to the server. This grants unauthorized access to the attacker while maintaining the illusion of a legitimate session. On the other hand, session ID prediction takes advantage of poorly designed token generation mechanisms. Some servers might use algorithms that create sequential or time-based tokens, making them easier to predict. For example, if session tokens follow a predictable pattern, such as increasing by 1, like 1001, 1002, 1003, an attacker only needs to observe the sequence to guess the next token. Similarly, tokens based on timestamps might reveal clues if the attacker understands the format and timing of the generated token. Attackers also resort to brute forcing session IDs when the range of possible values is limited. For instance, if tokens are simple 4-digit numbers, it takes just 10,000 attempts to try all possible combinations. Without proper rate-limiting mechanisms, this method can be alarmingly effective. Additionally, if the server uses weak random number generators to produce tokens, attackers can predict future tokens by analyzing how they are generated. The attacker's strategy typically begins with acquiring valid session IDs, studying their patterns, and predicting or brute forcing the next token. Once they obtain a working token, they insert it into the session data to hijack the user's identity and gain unauthorized access. This highlights the importance of secure practices like encrypting traffic with HTTPS, using robust random number generators for tokens, and implementing rate limiting to prevent brute force attacks. Let's see two sophisticated techniques attackers use to compromise session IDs: the man-in-the-middle attack and the man-in-the-browser attack. In a man-in-the-middle attack, the attacker places themselves between a client and a server, intercepting and controlling the communication flow. They split the original TCP connection into two, one between the client and the attacker, and another between the attacker and the server. This allows the attacker to monitor, alter, and even inject fraudulent data into the communication. For example, during an HTTP transaction, the attacker can intercept sensitive data like session IDs and manipulate the interaction to their advantage, all while maintaining the appearance of a legitimate connection between the client and server. The man-in-the-browser attack takes this concept further by leveraging malicious software, such as a Trojan horse, to manipulate communications within the user's browser. Unlike the man-in-the-middle attack, which intercepts external traffic, the man-in-the-browser attack operates inside the browser itself. The Trojan installs malicious code that integrates with the browser, remaining invisible to both the user and the web application. Here's how a typical man-in-the-browser attack works. First, the Trojan infects the system and embeds malicious code into the browser's configuration. Then, when the browser is restarted, this code activates, monitoring user activity and targeting specific websites. Upon detecting a targeted site, the Trojan captures sensitive data such as login credentials or session IDs and modifies transactions in real time. Then, the attacker can manipulate data fields, such as altering payment amounts or account numbers, while the user remains unaware. Finally, the server processes the fraudulent transaction and generates a receipt, which the browser displays to the user with unaltered details, reinforcing the illusion that everything is normal. This technique is particularly dangerous as it can bypass traditional security measures like SSL encryption, public key infrastructure, and even two-factor authentication. Since the attack occurs within the browser, the external security mechanisms cannot detect the manipulation. It's most commonly employed in financial fraud, targeting online banking systems to alter transactions for monetary theft. Let's break down compromising session IDs using client-side attacks. Client-side attacks are a clever way attackers exploit vulnerabilities in applications like browsers, Java environments, or messaging apps. These attacks often trick users into interacting with malicious links or websites, allowing attackers to steal sensitive information such as session IDs. One common method is cross-site scripting, or XSS. In this attack, malicious JavaScript is injected into a vulnerable web page. When you load the page or click a crafted link, the script runs without you realizing it. For example, it might silently grab your session ID, used to keep you logged in, and send it to the attacker. Once they have your session ID, they can impersonate you on the website. Another method is cross-site request forgery. Unlike cross-site scripting, which tricks the user, cross-site request forgery exploits the trust a website has in your browser. Here's how it works. The attacker sets up a fake web page with a hidden malicious form. You, thinking it's legitimate, interact with it, maybe logging in or clicking a button. When you submit the form, it's sent to the real website using your active session, which the website trusts because it sees the request as coming from you. The server accepts the request and performs the attacker's action, like making purchases or changing your account details, all under your name. These attacks are silent but powerful. They rely on users unknowingly assisting the attacker. Session replay attacks are another sneaky method attackers use to compromise session IDs. Here's how it works. Imagine you log into a website. During this process, your browser sends an authentication token to the server as proof of your identity. This token is unique to you and keeps your session active. However, if an attacker is eavesdropping on the communication between you and the server, they can capture this token. Once they have your authentication token, the attacker doesn't need your password or any other credentials. They simply replay the token back to the server, making it seem like they're you. The server, trusting the token, grants them access to your account. It's like overhearing someone say, "I'm Joe, let me in," and then walking up and saying the same thing to get access. To prevent session replay attacks, websites often use measures like encryption, for example, HTTPS, to ensure tokens can't be intercepted. They might also use mechanisms like time-limited tokens or one-time use tokens that expire quickly, making captured tokens useless to attackers. Let's talk about a clever but sneaky attack called session fixation. It's a way hackers can hijack your session without even stealing your session ID. They actually make you use theirs. Here's how it works. First, the attacker connects to a website and gets a legitimate session ID from the server. This session ID becomes their trap. Next, they share a link containing that session ID with you. Maybe it looks like an official email or message, something like, when you click the link, you're taken to the website's login page. Since the session ID is already valid, the server doesn't bother generating a new one. You log in, and voila, you've unknowingly logged into the hacker's session. Now, the attacker knows the session ID you're using. Because it's the same one they set up, they can now access your account and do anything you can, like view sensitive information, make changes, or even steal money if it's a bank account. This works because some websites don't generate a fresh session ID after someone logs in, which makes them vulnerable to this type of trick. Hackers use different tricks to fix their session ID on your browser. They might embed it in a URL, hide it in a form field, or set it through cookies. Imagine this scenario. The attacker connects to a banking website and gets a session ID, like 12345. They send you an email saying, "Urgent, update your bank details here," with a link that contains their session ID. You click the link, log in, and now you're logged into the attacker's session. The attacker, already knowing the session ID, uses it to access your account and take over. The scary part? You might not even realize what happened because the website behaves as if nothing's wrong. To stay safe, be cautious with links, especially those containing session IDs or that look suspicious. Always log out after using a shared or public computer. Website developers should ensure their systems generate a new session ID every time a user logs in, no matter what. Session fixation might sound tricky, but with some precautions, you can avoid falling into this trap. Now let's talk about session hijacking using proxy servers. In this attack, the attacker tricks the victim into clicking on a fake link that looks legitimate but actually redirects the victim to the attacker's server. Once the victim interacts with this link, the attacker essentially becomes a middleman or proxy between the victim and the legitimate server. Here's how it works. The victim clicks on the malicious link, which appears safe, but the link actually leads them to the attacker's server. The attacker, now acting as a proxy, sends the victim's request to the real server on their behalf. As the middleman, the attacker can capture session information from the ongoing communication between the victim and the server. This could include sensitive session IDs, cookies, or other authentication tokens. By doing this, the attacker can hijack the victim's session and use it to impersonate them, gaining unauthorized access to the victim's account or sensitive information. It's a dangerous tactic because the victim doesn't realize their session is being intercepted. The attacker can carry out malicious actions while the victim believes everything is normal. Let's talk about the crime attack and how it's used for session hijacking. The crime or compression ratio info leak made easy. Attack targets vulnerabilities in the compression mechanisms of secure web protocols like HTTPS, SSL, TLS, and SPDY. This type of attack is particularly dangerous because it exploits weaknesses in the data compression process, which is used to reduce the size of data before it's encrypted. Here's how the attack works. When a user establishes a secure HTTPS connection with a web server, the communication is encrypted using TLS, which is designed to protect the data from eavesdropping. As part of the authentication process, the server sends a cookie containing the user's session details. This cookie is essential for identifying the user in future requests. In HTTPS, cookies are compressed using a lossless compression algorithm like deflate before they are encrypted. This compression makes it difficult for attackers to directly capture the cookie by simply sniffing the traffic. However, the crime attack takes advantage of how compression works. For the attack to succeed, the attacker needs to trick the victim into visiting a malicious website. Once the victim clicks on the malicious link, they are either redirected to the attacker's site or malicious code is injected into their system. If the victim has already established a secure connection with the web application, the attacker can use techniques like ARP spoofing to intercept the HTTPS traffic between the victim and the server. The attacker can then manipulate the HTTPS requests by adding random characters to the cookies. By analyzing the responses from the server, the attacker can detect small changes in the length of the encrypted cookie based on the way compression works. These changes allow the attacker to predict the actual value of the authentication cookie. Once the attacker has obtained the cookie, they can impersonate the victim by sending the cookie back to the server, hijacking the victim's session. This gives the attacker access to sensitive information such as passwords, bank account details, and personal data. Let's take a look at a session hijacking technique known as the forbidden attack. A forbidden attack is a type of man-in-the-middle attack that exploits a vulnerability in the use of cryptographic nonces during an HTTPS session. A nonce is a random value that is used only once in cryptographic processes, specifically in the TLS handshake when securing a connection. According to the TLS specification, nonces are meant to be unique and never reused. However, when a TLS implementation incorrectly reuses the same nonce, it opens the door for attackers to perform a forbidden attack. Here's how the attack works. The attacker begins by monitoring the connection between the victim and the web server, focusing on sniffing the nonce used during the TLS handshake. Once the attacker has captured the nonce, they generate their own authentication keys based on the reused nonce. This step allows them to hijack the secure connection. After gaining control of the session, all traffic between the victim and the web server flows through the attacker's machine. At this point, the attacker has the ability to inject malicious content into the communication. The attacker can inject harmful elements, such as JavaScript code or fake web fields, into the transmission. These elements are designed to trick the victim into revealing sensitive information, such as passwords, bank account numbers, or social security numbers. The key to this attack is the reuse of the cryptographic nonce. which is supposed to be unique for every session. By exploiting this flaw, attackers can bypass security protections, hijack the connection, and potentially steal critical personal information. Finally, let's talk about the last application-based attack, session donation attack. Now, we're reaching the end of our discussion on application-based attacks, and this one's called the session donation attack. It's a pretty sneaky one, where the attacker essentially donates their own session ID to a target user. Here's how it works. First off, the attacker logs into a service, like a bank website, and gets a valid session ID. This session ID is like a ticket to their account, allowing them to access everything they need. Now here's where it gets tricky. The attacker sends that session ID to the victim. They do this by creating a link, could be through a method like cross-site scripting, or even through a man-in-the-middle attack. The victim, thinking it's a normal, trustworthy link, clicks on it. When the victim clicks on the link, they unknowingly open a page in their browser. But here's the catch. The session ID the attacker gave them is now active in their browser. So when the victim enters their personal details, like their login credentials or payment information, it's actually linked to the attacker's account, not theirs. The victim may think they're logging in or making a payment as usual, but in reality, the attacker now has access to all the sensitive information the victim enters. It's like the attacker is sitting in the victim's chair with all the details they just entered. And just like that, the attacker has hijacked the session without ever needing to steal any credentials directly. Pretty wild, right? So, that ends our look at application-based session hijacking attacks. We've covered a lot of ground today, and hopefully you have a better understanding of how these attacks work. So, let's dive into network-level session hijacking. This type of attack is especially popular because it doesn't require an attacker to have access to the victim's host, like in host-level hijacking, and it also doesn't need to be tailored to a specific application, as is the case with application-level hijacking. This makes it a more general and versatile attack. Network-level hijacking targets the transport and internet protocols that web applications rely on. By attacking the network layer, attackers can gather critical information that can later be used to target sessions at the application level. There are different ways an attacker can hijack a session at the network level. Some common techniques include blind hijacking, UDP hijacking, TCPIP hijacking, RST hijacking, man-in-the-middle attacks with packet sniffers, and IP spoofing with source-routed packets. To understand how network-level hijacking works, it's important to know about the TCP three-way handshake. This is how two machines establish a connection over the internet. When Jordan, the victim, wants to connect to a server, he sends a packet with a SYN flag to the server to begin the connection. The server responds by sending a packet back with both the SYN and ACK flags, along with an initial sequence number, ISN, for the server. Jordan then sends back an acknowledgement, incrementing the sequence number by 1, which finalizes the connection. At this point, the connection is established and the two machines can communicate. They can close the connection either by using the FIN flag for a graceful close or the RST flag for an immediate reset. The key to understanding this from an attacker's point of view lies in the sequence numbers that are part of the connection process. While it's easy to determine the victim's IP address and port numbers because they're visible in the IP packets, the sequence numbers change and need to be predicted. In a blind hijacking, an attacker doesn't directly see the sequence numbers, but they can try to guess them based on patterns or other data. If they guess the correct sequence number and send spoofed packets, they can trick the server into accepting those packets as if they came from Jordan. So, to put this into perspective, Jordan starts the connection by sending a packet with a SYN flag. The server responds with a SYN plus ACK packet that includes its sequence number. Jordan then acknowledges the server's packet with an ACK and the connection is established. If the attacker can predict the next sequence number and ACK number that Jordan will send, they can spoof Jordan's address and communicate directly with the server, hijacking the session. And that's the basic idea behind network-level session hijacking. It takes advantage of how connections are established and how sequence numbers are used to ensure the integrity of the communication between Jordan and the server. Now let's talk about TCPIP hijacking. In a TCPIP hijacking attack, the attacker intercepts an already established connection between two parties by using spoofed packets and then pretends to be one of those parties. Essentially, the attacker inserts themselves into the communication between the victim and the target server, effectively taking control of the session. Here's how the attack works. The attacker sends spoofed packets with the victim's IP address to a machine that's already in communication with the victim. If the attack is successful, the attacker can intercept and hijack the connection, forcing the victim's machine to redirect the traffic to the attacker's own machine. The victim doesn't know this is happening, and their connection with the server hangs while the attacker takes over and communicates with the server on the victim's behalf. To launch a TCP/IP hijacking attack, the attacker and the victim must be on the same network, though the target server can be anywhere. This makes systems that use one-time passwords especially vulnerable, as the attacker can easily spoof the victim's connection and bypass authentication measures. Now, the attacker continuously sends spoofed packets from the victim's IP address, keeping the server's communication alive while the victim's connection is essentially frozen. Through this process, the attacker can hijack the connection, interact with the server on behalf of the victim, and potentially gain unauthorized access to sensitive data or systems. Let's talk about IP spoofing using source-routed packets. This technique allows an attacker to gain unauthorized access to a computer by pretending to be a trusted host using its IP address. It's a crafty way to hijack a session by tricking the server into believing it's communicating with the legitimate user. Here's how it works. The attacker spoofs the IP address of a trusted host that's already in communication with the server. Normally, the server would only accept packets from this trusted host, but by using source-routed packets, the attacker specifies the exact path for their forged packets to travel to the destination. This gives the attacker control over the route and fools the server into thinking the communication is legitimate. Once the attacker successfully spoofs the trusted IP address, they manipulate the sequence and acknowledgement numbers of the session. By altering these numbers, the attacker injects their own forged packets into the session, getting them processed by the server before the legitimate client has a chance to respond. This desynchronizes the session, as the sequence and acknowledgement numbers no longer match between the legitimate client and the server. From here, the original packets sent by the actual user are ignored or lost, and the server instead processes the attacker's packets with the new sequence numbers. These packets are routed according to the attacker's specifications, allowing them to redirect communication to a patched destination and take over the session entirely. This type of attack is particularly dangerous because it doesn't just hijack the session, it actively disrupts communication between the legitimate client and the server, leaving the attacker in full control. Let's delve into a few techniques used in network-level session hijacking. These methods highlight just how attackers exploit weaknesses in communication protocols to disrupt or take over connections. First, we have RST hijacking. Here, an attacker injects a reset or RST packet into an ongoing connection. They use a spoofed source IP address and predict the correct acknowledgement number to make their packet look legitimate. If they guess right, the victim's machine believes the reset is authentic and immediately terminates the connection. Tools like Colasoft Packet Builder or TCP Dump make it easier for attackers to craft and analyze packets for such attacks. Finally, there's UDP hijacking, which takes advantage of the user datagram protocol's lack of sequencing and synchronization. Since UDP is connectionless, it's inherently easier to exploit. An attacker can forge a server's response to a client's request, taking control of the session before the legitimate server has a chance to respond. This can be further enhanced with a man-in-the-middle attack, allowing the attacker to block the legitimate server's reply entirely. Here's how UDP hijacking generally works. First, spoofing the source IP address. Because UDP doesn't have a handshake mechanism, attackers can simply send packets pretending to be from another host. Then, they intercept the traffic. They insert forged packets into the communication stream. These packets appear to come from a legitimate source, but carry malicious payloads. Finally, they manipulate the communication. By injecting false data or unauthorized requests, attackers can alter the application's behavior or gain unauthorized access. All right, now let's dive into some tools commonly used for session hijacking, starting with Burp Suite. Burp Suite is one of the most popular tools among security professionals. It's a comprehensive platform for performing web application security testing, including session hijacking. Burp Suite allows attackers, or testers, in ethical scenarios, to intercept, modify, and forward HTTP and HTTPS requests. It can be used to capture session tokens, analyze them, and even manipulate them to hijack a session. From capturing cookies to replaying requests, Burp Suite makes it easy to interact with web traffic at a granular level. It's an essential tool for penetration testing and can also be used to assess vulnerabilities in session management systems. I have video about full guide on Burp Suite. You can check it out. Okay, another tool we should talk about is HeHe. HeHe is a really useful toolkit designed for HTTP security research. It's simple, but packed with features that make it great for testing and analyzing web applications, especially when it comes to session hijacking and network security. One of its key features is that it works as a machine-in-the-middle HTTP proxy. This means HeHe sits between the client and the server, allowing you to intercept and log all HTTP traffic. You can also use advanced search tools to easily find specific requests or responses that you're looking for, which is really helpful when you're analyzing large amounts of data. Another cool feature is the HTTP client it provides. With this, you can manually create and edit HTTP requests, as well as replay any intercepted requests. This is useful if you want to see how the server reacts to different modifications, such as changes in session tokens or headers. HeHe also gives you the ability to intercept requests and responses during the flow of communication. You can stop the traffic, review it, edit it if needed, and then either send it, cancel it, or modify it before sending. This can be a real game changer for spotting vulnerabilities in session management or web application security. Another tool worth mentioning is Kaido. Kaido is a web security auditing toolkit that security professionals use to intercept and inspect HTTP requests in real time while browsing. It's designed to help you analyze and manipulate web traffic, making it an invaluable tool for penetration testing and vulnerability research. One of the key features of Kaido is its ability to customize and test requests using large word lists. This allows security researchers to perform automated testing on web applications by injecting a wide variety of input values to uncover potential vulnerabilities. Kaido also lets you modify incoming requests using regex rules. This means you can set up automatic alterations to the requests in real time, which is especially useful when you're trying to exploit specific patterns or test certain input conditions. Additionally, Kaido provides the ability to resend requests to manually test specific endpoints or actions. This allows you to explore how the web application behaves with modified requests, which is critical when testing for issues like session hijacking or parameter tampering. Overall, Kaido is a powerful and flexible tool for web security professionals. It gives you the control you need to inspect, modify, and test HTTP traffic to ensure that web applications are secure from potential attacks. Our last tool is BetterCAP. BetterCAP is a portable framework written in Go that is widely used by security researchers, red teamers, and reverse engineers to conduct reconnaissance and execute a variety of attacks on different networks and devices. One of its standout features is its support for Wi-Fi networks, where it can be used to monitor and intercept network traffic, perform man-in-the-middle attacks, and even inject malicious packets into the network. It's also capable of targeting Bluetooth low-energy devices, making it a versatile tool for attacking modern wireless devices. Additionally, BetterCAP supports wireless human interface devices, enabling the manipulation of input devices like keyboards and mice, which could be useful for physical security testing. BetterCAP isn't limited to wireless networks. It also supports IPv4 and IPv6 networks, providing an all-in-one solution for network attacks. Whether you're testing the security of Wi-Fi networks, exploring vulnerabilities in Bluetooth devices, or conducting a red team engagement, BetterCAP is an essential tool for anyone looking to perform in-depth network security assessments. Okay, So those were some tools for session hijacking. And don't get me wrong, there are plenty more out there. But for now, this list is enough to get you started and give you a solid understanding. Now, before we end up this video, let's talk about something even more important: how to protect yourself from these attacks. After all, knowing how to defend against them is just as crucial as understanding how they work. First, make sure you're using secure connections like SSH or VPNs for sensitive communication. Always pass your authentication cookies over HTTPS to prevent them from being exposed. And speaking of cookies, protect them with settings like HTTP only and same-site attributes to limit unauthorized access. Now let's talk about sessions. Regenerate session IDs after every successful login and use strong random session keys. Don't ever put session IDs in URLs. They're way too easy to steal. Instead, rely on secure encrypted storage for these identifiers. It's also super important to encrypt all data in transit with protocols like SSL, TLS, or IPsec. This ensures that even if someone intercepts the data, it's useless without the decryption key. And while we're at it, make sure your browsers, apps, and systems are fully updated to fix any vulnerabilities that attackers might exploit. Another good practice is to implement session timeouts. This automatically logs users out after a period of inactivity. And if you're working in a network environment, switch from a hub to a switch-based network to reduce the risk of ARP spoofing. On top of that, educate your users or yourself to always log out of applications, especially on shared or public devices. Using unique, strong passwords for each account is another simple but highly effective step. And for extra security, enable multi-factor authentication. This makes it harder for attackers to exploit stolen session tokens. Lastly, keep an eye out for suspicious session activity, like logins from unusual locations. Implement security measures, like or behavioral biometrics, if you notice anything off. These tips aren't exhaustive, but they're more than enough to get you started on keeping your sessions and your data safe. All right, we end our today's video. I hope you found this topic valuable and learned something new. As always, if you haven't subscribed yet, go ahead and hit that subscribe button. It really helps out. Got any questions? Feel free to drop them in the comments, and I'll be happy to answer. And if you enjoyed this video, a like would mean a lot. Thanks for watching, and I'll see you in the next one.